welcome to everyone who's listening to us and watching this presentation. So I'm very glad and happy to introduce Torsten Hoefler as our speaker today. Torsten did his PhD in computer science in 2008 at Indiana University, and then had a professorship there also. Then he went to Zurich, where he now directs the Scalable Parallel Computing Laboratory. And Torsten has served as lead performance modeling and analysis in the US NSF Blue Waters project, and has held visiting positions at Argonne National Laboratories, Sandia National Laboratories, and Microsoft Research Redmond, where he also spent a couple of months at the end of last year. And his research aims at understanding the performance of parallel computing systems, ranging from parallel computer architecture through parallel programming and algorithms. And he's also active in the application areas of weather and climate simulations, as well as machine learning, with a focus on distributed deep learning. In those areas, he has coordinated tens of funded projects and an ERC starting grant on data-centric parallel programming. So I'm very grateful that Torsten can make it today, at least virtually, and I'm looking forward to his presentation.
Thank you, Martin. So I hope everybody can hear me. This is actually the first time I'm doing a webinar. I'm trying to speak as clearly as possible, and I hope that the technical problems that we just had with my laptop don't persist. So yeah, I'm planning to talk about high-performance communication for parallel and distributed deep learning today. And the idea is really to give an overview of what deep learning is and what the computational characteristics of deep learning are, and especially focusing on what the communication bottlenecks in large-scale deep learning are. I mean, first of all, motivate that actually deep learning is a very complex process that requires a lot of compute, at least in the foreseeable future. And this is something that my lab and I, and under the lead of one of my wonderful postdocs, Tal Ben-Noon, has been researching since a couple of years now. And we wrote this survey on demystifying parallel and distributed deep learning, which you can see on the page, on the slide, that is now published in the computing surveys, which basically summarizes everything. But this is not, so this talk is a subset of this, but it's not going to be the full survey, because the survey is about 60 pages in its full version, so it's more like a book, and I can only summarize a small subset. But let me get started. So what is deep learning good for? And I think I don't need to talk a lot about this because we all know it. It started in the late 80s on digit recognition, then we'll move to object classification, segmentation later, image captioning getting more and more complex. We actually went to gameplay and trying to understand trying to play games better than humans. Then we went to neural computers, which is a very interesting phenomenon where we try to learn little programs and neural Turing machine. And more recently, actually in the last 2 years, we went to gigantic language models, which actually some people claim that we could solve something like general human intelligence with these models, in the sense that we can understand the body of knowledge we have in the internet. And once you have that understanding, you could, of course, go further. And then very recently in 2019, these models have been used, led by OpenAI, towards real physics simulation and trying to understand an environment that is as close as possible to reality as we know it today. And then it gets quite scary, because if we extrapolate this towards 2030 or so, then we may have general intelligence that understands physics. And then if we mount this on a robot, then it gets interesting. But that's the future. So what we have today are actually all these industry and cloud providers that are using deep learning in one way or another, and no matter what we do. For example, this video, I'm pretty sure that's recorded right now, that will definitely go through 1 or 2 deep neural networks later. So at the end, deep learning is an extremely active area of research, and we can just see this by the number of publications in this list going back to 2012. So interestingly, there are these 2 fields, CS.ai, this is data from arXiv, and CS.cv, so artificial intelligence and computer vision. And we can see an extremely strong growth rate. And we are currently in 2020 at a rate of about 42 papers per day in that field. And that's, of course, impossible to follow for everybody. And this is why In this talk, we're summarizing the subset of these papers that are dealing with large-scale deep learning methodologies. But first, let me introduce a little bit more how deep learning works. And for some of you, this may be new. For some of you, this may be a repetition, but then it'll definitely give you a different perspective. So what deep learning is really it takes a massive data set. In that case, I've just talked about, by the way, if you look at this computer vision, we see that this is vastly outnumbering the general AI workload. So computer vision is one of the most popular deep learning states. And as I mentioned, we are now moving towards natural language processing and more use in the natural sciences that I will talk about later. So let me focus on computer vision. So we have a large data set with a lot of images, essentially, or videos. And we have a network that is a fixed structure. So you can see here, this is AlexNet, and this fixed structure is basically a computational structure. It defines a computational graph. We take one of those images, and we run it through that computational graph. So as implemented by that fixed structure. Then at the end, what this fixed structure and the weights in that structure implement is a function that we call f of x. By the way, deep learning at the end is nothing but probabilistic or stochastic function approximation. So we want to find this function f of x, which takes as an input an image and outputs a classification in this particular case. And this classification should be as close as possible to the true classification. And here in the true classification, every human immediately understands that this is supposed to be a cat. But now, as we can see, this classification that the deep neural network outputs on the left side, this is a probability, basically, for how likely the network thinks that this is a cat, a dog, an airplane, and a horse. And so we can see it's not perfectly classified as a cat, so it could also be a horse in this particular case, or a bit less likely, but still. And then what we do in order to improve the prediction quality of the network, we basically take the ground truth, which is the right side. So here it's a probability 1 the cat and 0 everything else, and then update the weights of this fixed structure going backwards. And I'll talk about what a weight is in a couple of minutes. And so we do this in an iterative process that is called training. And then once we converge this training, after lots and lots of iterations, looking at the whole data set, sometimes also called epochs, then we are happy with an implemented function, and then we use this function in prediction, and this is typically called inference. Okay, so if you look at sizes, it's now getting interesting. So these images, these image data sets, they can be pretty large. So 180 gigabyte is what is ImageNet today, the standard one. A one with larger, so ImageNet 22K, with a larger number of classes and more images can go up to terabytes. And in fact, industry has several petabytes of data that is analyzed today. You can easily see this if you just look at the published images on Instagram, for example. These deep neural networks themselves, like these computational structures, they can be quite interesting. They can be quite deep. So they can be hundreds of layers deep. They can have up to billions of parameters, and I'll give you some more examples. And these billions of parameters can have multiple gigabytes of parameter storage. So these objects can be quite compute intensive, so that they, for example, don't always fit your cell phone, but there are also small ones that fit your cell phone. So here's another visualization of the accuracy on the y-axis versus the operations required to evaluate the network in the inference case versus the size of the of the circle here. And as you can see, as the accuracy goes up in general, the size also goes up. And then the number of labels or the number of classes at the end is somewhere between 10 and 20,000, and it's of course growing, because eventually every single person on the planet, so each of us may be a label, because if we want to do person recognition or face recognition, then we will all be labels in this sense, in this space. So what this means really that deep learning is supercomputing. So we require a lot of compute to do this. And if you're not believing me, then let's look at this graph published by OpenAI a couple of months back, where they look at the history of learning and then more recently deep learning, beginning in the 1960s with a perceptron, single layer perceptron, going to the late 2010s into 2020. So on the y-axis, we see petaflops per day required to train a network. So here is, for example, in this line would be 1 petaflop a day required to train any network on this line. So there is none on this line, but you can see there are some that are already more expensive. And what OpenAI defines is basically a first era of deep learning, which ends about 2012, and then, or maybe 2013, and then the modern era of deep learning. And the major difference between these two eras is that the first era was actually following Moore's law scaling, so every 18 months doubling, or in this case, they say 2 years, doubling the performance, so the capability to train a model at equal cost. And in the modern era, it's more interesting because there we have a doubling every 3.4 months, which basically means every year there's a factor of 10 higher compute power available to train these deep neural networks. And this is mostly due to architectural innovations that we have today, and due to the willingness of industry to invest much more money into training deep neural networks than it was in the past, because they have shown much more promise as they've shown in the past. So, for example, AlphaGo Zero was a major breakthrough for the computer to learn to play Go. Neural machine translation was a similar breakthrough. Dota was a very astonishing result where a deep learning model learned to play a game that is very close to real physics, as good as humans can play it, and was actually winning the championship of Dota. That's called the one-on-one, so one player against another worldwide, which is actually quite a popular championship. So just a couple of weeks ago, Microsoft published the largest trained model so far, which is a so-called transformer language model. And the idea here is similar to what I mentioned earlier. You ingest a very large corpus of text, so usually gathered from the internet, and somewhat remember the statistical distribution of this text corpus. And this network was trained with 17 billion parameters. So just storing this trained network would require 68 gigabytes of memory if we store it in FP32. So that's quite a massive model, and in fact the largest model trained so far. So that's the storing group at Microsoft that I've been with. So now, if you look a little bit more at the theoretical side, so as I mentioned, we have this function f of x that we want to train. And we have an input. These are labeled samples, and I introduce some notation here. We have a label domain y, and we have the true label, which we call L of x. And eventually, we want to learn this function x that maps from the labeled samples to the label domain. Right? So it's a quite simple problem. What's super fundamental about this function x is that it has two pieces. It has a fixed network structure, as I mentioned, this AlexNet in this example, and it has a learned number of weights. So this is fundamental to deep learning. So usually you design the network structure, or you choose it somehow, and then you train the weights in this iterative training process. And if you look at the loss functions here, if you actually look at the okay, what is a loss function? A loss function is the function that we use to train the network. So it gives us some kind of distance metric between the prediction of the network and the true label. And there are many of these different loss functions that I don't want to go into details here, because that's a whole machine learning course by itself. But this basically gives me a distance metric, and in the layer-wise update rule, as we go backwards in the network, we apply this distance metric to correct the weights. And what's now the optimization goal is we want to find the optimal set of weights, W star, which is what we learned during the process, that minimizes the distance as defined by the loss function. So there are multiple loss functions, candidate loss functions, for an arbitrary example drawn from the distribution D, which is our space that we draw the examples from. And overall, so we want to minimize the expected loss over the distribution, or over examples drawn from the distribution. And the way we implement is in this layered approach that I mentioned before. This is why it's called deep learning. So these are nested functions. So the function is expressed as a set of nested functions. So f of n minus 1, of f of n minus 2, and so on. And these are typically drawn as layers. And the first one is f1, and then f of 2, f of 1, and so on. So the output of f1 moves into f2, and so on. And at the end, once we have it evaluated towards the final function, we have the full function f of x. So this is how it works. And each of these functions has usually a nonlinearity piece to it, which then basically means that that gives it the computational power. So if these were all linear, then we could basically replace this by a single layer. but the nonlinearities give us a lot of computational representation or method representation. Okay, so how does the training now work? And this is quite important to understand the computational properties. So you can now solve this equation up here, this minimization, with any arbitrary approach. You could use gradient descent. You could use second-order methods like the Newton method. You could use anything basically. So even genetic algorithms or things like this have been tried. Basically, everything on the planet has been tried, and the most successful training mechanism is called the stochastic gradient descent algorithm, which is a gradient descent method that draws random examples to descend towards the loss of these examples. So how it usually works, it's an iterative algorithm. So we run for a couple of iterations. We draw a random element from our test set, or from our example set. Then we apply all these layers in a forward evaluation, as I just mentioned. So just this is normal inference, essentially. And then we take a loss function and we compute the gradient. So basically the difference we want to correct the weights by in a backward pass using the chain rule, just standard differentiation. And then we update weights at each of those layers iteratively with some update function. So we compute the weights at time step t+1 from using the weights at time step t, and then some update function based on the gradient of time step t and potentially all earlier weights and potentially the time step itself. So these update functions are actually a lot of the magic in deep learning. So which means that I again cannot explain them in detail. Please refer to the survey that we show down here, or refer to any favorite deep learning or machine learning textbook where you can find these rules explained. But these are actually extremely critical. So then, of course, we need to store all these parameters, outputs, or sometimes called activations, and gradients of weights and for each layer. And so this is quite important for the computational properties of this function. Okay, so now we realize that this deep learning is actually quite an important problem. So the major vendor has been NVIDIA in this area, but basically every other company on the planet, like IBM, Google, Intel, so every company that makes some kind of silicon has been developing specialized chips for deep learning. So this is quite interesting to just observe that field, because it is moving amazingly fast. It's moving so fast that it's probably the fastest growing field in computing currently, because there is such a big potential in this area. So I would just like to remind us of that industry power behind deep learning in general. So what we've done is we've actually looked at hardware trends in deep learning in this analysis. So the method we chose to do this, and this was mostly driven by my postdoc Tal Ben-Noon, is that we looked at about 227 papers in parallel deep learning, and we classified each of these papers, beginning first by the year they were published in, and then we classified what kind of architecture they use: CPUs, GPUs, FPGAs, or specialized architectures. And what we can clearly see is that GPUs are somewhat dominating until 2017. If you look at the more recent trends, we see more movement towards specialized architectures. Furthermore, what we could also see is in the same analysis, now with a different metric, we looked at whether these papers used single node experiments or ran the experiments on multiple nodes. And what we could see is it was extremely quickly growing towards multiple nodes. So the conclusion is that today, deep learning is largely on distributed memory, which is quite important. So, which means that the computational power required to train a network is in fact larger than a single node can sustain. So now the question is, how many nodes are we using for deep learning? And we looked similarly again through the papers, so these 200 papers, and we looked at how many nodes are used to train deep neural networks. What we can see in the good old early days, there was quite a large number of nodes used. In fact, this disbelief network used several thousand nodes. And then it seemed to compress until 2013, so using less nodes. And this is attributable to the advent of GPUs, because Stanford showed that, or a group of Stanford showed that you can actually achieve a very similar training result, similar performance, based on a much smaller cluster. And instead of a couple of thousand nodes, you use tens of nodes of GPUs instead of standard x86 CPUs at the time. And then this trend went down until 2015, basically using more and more GPU systems, more and more accelerated systems, before the surge started again, going up until today with a very high growth rate. Here, using the full Titan supercomputer to perform learning of some models, actually model search in this example, because we need more and more compute to train these large models. And this is also what we've seen in this OpenAI picture early on. Furthermore, the question is, what kind of communication system do these papers use? Again, same scale there, 2013 to 2017. And we see that most of them are beginning to use MPI, and some of them remain with sockets, but of course, yeah, we can't help those because this is fundamentally inefficient. But we can see that most of them are converging to MPI. And this is also quite interesting. If you know my background, I'm one of the MPI people working mostly on MPI 3 in my previous career. So this is why I will later in the talk about what we can do for the communication in deep learning once we've understood all the background. So, of course, I lied to you at the beginning when I explained stochastic gradient descent to you, because this is not what anybody is using today. Because I told you that we draw one random element from the input set x, which is not fully true, because what we do is the so-called mini-batch stochastic gradient descent, which means we are drawing a vector of random elements from the input set x, and then apply each of these operations that I told you about earlier in a kind of a vectorized form. The benefit of this is that we can transform BLAS2 routines, so matrix vector operations, to BLAS3 routines, matrix operations, which makes it much more efficient to execute this computation, and also gives you slightly better statistical properties, as we'll see in it. So this is mostly done, but the mini-batch is mostly done for computational efficiency. And there's now an interesting trade-off that we need to be aware of. If you're a deep learning practitioner, this is probably one of the most important trade-offs. This is the trade-off between performance and validation error as mandated by the mini-batch size. So there are three regions that we could look at, A, B, and C. So in theory, A does not exist, but in practice it has been shown by several papers. And the idea here is that the validation error goes down if you increase your mini-batch size. So mini-batch size 1 is not necessarily the best, but generally small mini-batch sizes give you the smallest validation error. Right? But small mini-batch sizes also give you the lowest performance. And now the question is, in practice, actually, for running larger and larger models on larger and larger systems, how big can we make the mini-batch size? Because the larger the mini-batch size, the better our performance gets, as you can see in this comic, until we lose too much of the validation error. Because at the same time, if I'm increasing the mini-batch size, asymptotically, I will just use the full batch, right? I will use all my examples in the maximum mini-batch size. But then I have no stochasticity in my stochastic gradient descent, and it's simply called a batch method. So it's non-stochastic in this sense. And then, of course, I'm losing all these nice properties that come from the stochasticity, and I will find a less good solution at the end. So the trade-off is trying to find the task is trying to find the largest possible mini-batch size that gives us a reasonable validation error, which is incredibly hard in practice. It's incredibly problem and network dependent. So this is something we can't really talk generally about, but that's the goal. So then I want to tell you a little bit about the things that we've been doing on the computational side. So now each of these layers is implemented on a CPU or GPU. In this particular example, in cuDNN, we have 16 different ways to implement the convolution operation. So the convolution operation in a so-called convolutional neural network is an operation that is quite similar to a stencil. It just has an additional dimension, this channel dimension that is summed up on at the end. But it's relatively similar to a stencil, so it has a fixed shape and is moved over the input image and all the input channels of the image. And this implementation can actually be implemented in these 16 different ways, as I mentioned here, and there is a trade-off between the workspace size, so the size of the working memory of that implementation, and the execution time. And we can see generally the larger the memory we give to this layer evaluation function, the smaller the execution time. And this is all fine. Unfortunately, our GPUs have limited memory, so we cannot always use the largest workspace because they have to, you may say, 120 megabyte is not much, but many of those deep neural networks are pretty deep, so which means we need to have a lot of storage for these layers. So, I mean, a lot of layers in the GPU at the same time. So what we did is we basically segmented the Minibatch, which is our set of examples, into smaller batches, which we call microbatch, and reuse the workspace across different algorithms. And now the question is how we can choose the microbatch sizes in these algorithms, and then we have two approaches that I don't want to go into detail. But if you're interested, you can read this in this paper cited down here. We have a dynamic programming and an integer linear programming approach. I just want to get to the results. We get relative to existing approaches about 4.5 times faster on a benchmark that is called Deep Bench, simply by tiling, in this particular example, using the FFT algorithm or the Vinograd algorithm mixed with the FFT algorithm, as opposed to the implicit algorithm, which is the default and not, and in this case, if you look at here, the least space-consuming algorithm, but also the slowest. So, and then there are different strategies we can run this with, but this is one particular example how you can optimize the computation of deep learning on a layer-by-layer basis. So now let me talk a little bit about what the different forms of parallelization are for deep learning. So here on the left side, we again see our examples. So lots of images cut into 4 pieces. And we differentiate 3 different forms of parallelism. So one parallelism is what we call layer parallelism. So we take each of these layers. So this is layer 1, layer 2, and fully connected layer 3. So 2 convolutional layers. And the third layer is the fully connected one. And so in layer parallelism, what we do is we cut each of those layers into multiple pieces and process these pieces on different processors. As you can see here, the green, the blue, and the somewhat yellow or brownish processor. This is the first form. So this is quite a quite good parallelization scheme. This is in fact used for the implementation on vector units or in SIMT units on the GPUs. Vector units on CPUs and SIMT units on the GPU. So this is my finest grained form of parallelization where I now process the layer in parallel. So the second form of parallelism is quite an interesting one. Interesting trade-offs. It's called pipeline parallelism. And the idea here is that I do not cut the layers, but I cut across the layers. So I process layer 1 on CPU 0, GPU 0. I process layer 2 on GPU or CPU 1. I process layer 3 on CPU or GPU 2. This has the benefit that the communication is very limited because typically between those layers is a very small cut in these networks. And I can still distribute the parameters across the different processors. So like in the first case, I distribute parameters. And so I can solve larger and larger models with fixed size accelerators. But here the communication is slightly better. But of course, I still have to copy the Minibatch through all these. The last form of parallelism, the so-called data parallelism, is in fact the most used form of parallelism because it's also the simplest one to implement. What do I do here? I take different examples. So the first one that uses different examples and run these samples through 3 separate copies of a full network. So I basically instantiate my full network 3 times on 3 different GPUs or CPUs and just process these examples independently. Right? So of course the obvious benefit of this is extremely simple because I don't really need to deal with a lot of parallelism because I just copy my whole model to every single GPU or CPU. But the obvious downside is I need to copy my whole model to all my processors. So I have to have the whole storage replicated across all these processors. And I still need communication back. So if I was now going to implement a deep learning framework for parallel computation, what you would have to do is actually to use all these 3 forms of parallelism, data parallelism, layer parallelism, and pipeline parallelism together. In fact, most frameworks today offer data parallelism, which is a trivial form, and they offer layer parallelism at the finest grain. As I mentioned, through libraries, typically like cuDNN or cuBLAS, implement their parallelism. And pipeline parallelism is supported by some frameworks, but not all. It's still relatively new. It's also not too easy to use, and we can discuss this offline if you're interested. So now let me talk a little bit more about the most used form of parallelism, which is the distributed data parallelism. Right? This is the trivial one, as I mentioned. We just copy all these models, and this is what traditionally TensorFlow, PyTorch, implemented by Horvath in the good old days, use for parallelizing deep learning workloads. So there's now one way to synchronize these parameters, because of course these three copies, they will generate different parameter sets and they will generate different gradients. So if you look at, in this particular case here, 4 different training agents. Each of these training agents has a copy of the model. And then we implement a parameter server in the middle that keeps the latest copy of these the sets of parameters around. Right? So and at every single iteration, each training agent computes the new gradients, sends the gradients to the parameter server. The parameter server computes the new weights based on this update function u that I mentioned earlier on, and sends the new weights back to the training agent to go to the next iteration. And so this is how a parameter server would work. And if you're an HPC person, you would immediately see, oh my God, this is a very bad idea, because now if I'm running this on 1,000 training agents, all of these 1,000 training agents would need to talk to this one parameter server, even if the server is sharded, which means that different shards of parameters are at different servers. There is still 1,000 messages going into every single server. It's just small messages if it's sharded. And the obvious solution to this is, if you're an HPC person or an MPI person, is that you would take training agents, get rid of the parameter server, and in fact just implement a collective reduction of the weights or of the gradients, right, that we can then define. It's called, we can discuss this later. So this reduction is implemented by MPI. There are various optimizations that you can do, and I don't want to go too much into detail. Because in fact, MPI solves this problem pretty well. So there's not much to be discussed there. We shouldn't be inventing new all-reduce algorithms, at least not for the dense case. I will talk about some new algorithms, especially for deep learning. So now the interesting insight in deep learning is, in fact, that we do not need a fully consistent model. So what does this mean? If you go to the parameter server variant, these training agents send their gradient updates to this parameter server. But now, in practice, it's going to happen that some of these training agents are late, right? Because they're delayed by operating system noise or some transient performance invariance going on in this particular node. So what we could do in practice, what we would do with MPI, with a simple implementation, is we would run these different agents here. They would compute the weights of iteration number 1. Then they would synchronize with an all reduce, or in this case, not with an all reduce, but sending it to a parameter server. And then they would move into iteration 2, and so on. In the other extreme case, what we could do is we could have a fully asynchronous version, where we have a parameter server in the middle, and every agent just computes its new weights, sends this to the parameter server, and then receives the new weights from the new weight update from the parameter server, and moves into the next iteration, and so on. So every agent is fully asynchronous. There's no synchronization between those two. As you can guess, the left side is quite slow because we need to synchronize all these agents. The right side may or may not converge because these agents may run arbitrarily asynchronously. In fact, what is most promising is what we call stale asynchronous or bounded asynchronous, where the idea is that we let these agents run asynchronously until they exceed some threshold for the distance between those. So basically, this method makes sure that no agent runs ahead of the slowest agent for too much. Right? So this is well known since about 2011. It was actually quite funny because apparently the student of Chris Ray here discovered this, that by forgetting to correctly synchronize a shared memory implementation. So basically, the student was not correctly locking, was not correctly synchronizing. Then they found that this bug resulting from this incorrect synchronization was actually not changing results too much, but it was essentially giving the same result, but much faster than the correctly locked version. And this was later moved to disbelief to the distributed memory system. So this is what Jeff Dean at Google was introducing. And the fundamental idea here is really to trade off statistical performance, which is your model quality, for hardware performance, which is your speed or your costs to train the model. Right? Imagine, well, I can do exactly the same thing for the decentralized case. Right? So it's nothing different. So let me just move a little bit faster here. So here we have, again, the all-reduced synchronization, which could be fully synchronous, the stale all-reduced synchronization, where you could use non-blocking collectives to introduce a window of these all-reduces, or we could have a fully asynchronous collective where you could use gossip-style approaches, where you just send your weights to some other agent in the network at random, basically, I mean, randomly selected agent, and then hope that eventually the system will converge. And here it's the same result. The stale asynchronous and bounded asynchronous methods are actually best. And this is actually even more a wider spectrum. If you look at, we go from fully consistent to fully inconsistent. We have the synchronous, stale synchronous, and asynchronous. We could even go further and say, well, we are actually training models separately, right? And then average the weights of the model. Or what we could do every now and then, what we could do is we could train the models fully separately and then run every single example through all of these models and then use some averaging at the end. So we have ensemble learning, very much like we do ensemble methods in computational sciences, like in weather and climate analysis, and then choose some kind of statistical measure out of these ensembles to find the real result. So all of this is possible. And towards the right side, we get to more and more inconsistent parameters. Like in this ensemble learning, we have fully separate parameters for these different model copies. So now, as we learned about how to parallelize deep learning into various schemes to distribute the parameters and to run these in different synchronization modes, ranging from synchronous to fully asynchronous, I want to dive a little bit deeper into possible communication optimizations. Because if you look at the training in deep learning, the training process, you will see that the biggest in parallel and distributed deep learning, the biggest cost is actually the communication. So the bottleneck is almost always the communication. Only in some extreme cases it's not. And what is the communication about? As I mentioned, we send these gradients of the weights, and we receive the weights, at least in the common case. We could also send the weights themselves, but let's talk about the gradients here. So let me skip the second point here. That's a bit more complex. But what we could do when sending the weights, we could actually use lossy compression and accumulate the errors we are making when sending the weights locally. What does this mean? So we could, in fact, quantize the weights. So we could say, well, we have weights in 16-bit values or 32-bit values that we computed at each process, but we now round these weights using with the stochastic rounding technique. We round them down to a lower precision, like let's say 4 bits or even 2 bits, or actually in the extreme case, even 1 bit. Like there's a 1-bit stochastic gradient descendant, and this 1 bit basically just says go up or down, right? And then send only these quantized values. As you can imagine, 1-bit SGD works only for some specific cases. And as you add more bits, more and more cases will be enabled. And then there is a diminishing returns as you add more bits. So it's not necessarily clear what the exact bit count is, because that, again, depends on your problem and on your network size and on your training procedure. But this is something to be considered when you tune deep learning workloads. A second method, so this is quantizing every single value. The second method is actually to sparsify the gradients, because the size of the gradient is the exact same size of your model. So if we train a 17 billion parameter model, we actually have to send 17 billion parameters per iteration across the network if we do only data parallelism, from every node and to every node. So that's a whole lot. That's, as I mentioned, 68 gigabytes per iteration. What we could also do, of course, we quantize it down to a quarter of this or something, fine. But what we could also do is we could just send the principal components of each vector, so to say. So we pick the top k elements out of this vector. So let's say the top 1,000 elements, which means by top I mean the largest 1,000 elements at every single node, which is going to be different indices in the vector, right? And then we send those and reduce those. So this is something that is a bit more complicated, because now you need to still prove that this converges. In fact, a colleague and a collaborator, Dan Ellistar, has proved this. He's at the University of Vienna. And there's a paper on this that I don't want to go into detail, but you can actually prove that this works. You can show this empirically for several networks. And then you can implement this efficiently. And this is what we have done also in collaboration with Dan. And the idea here is that we support a reduction that we call the sparse all reduce. We form the global sum of vectors that are extremely sparse at each node. So what does this mean? Here is a vector of gradients at node 1, at node 2, at node 3, and at node 4. The shaded or black elements are the non-zero elements. The white elements are the zeros. And of course, the non-zeros are distributed according to the mini-batch the vector has, the node has seen. And that is different for each node, so these non-zero distribution is different. And as you now sum those up, zeros plus non-zeros are non-zeros, obviously, and then you densify the communication towards the pod. And so there's something to be gained, because in some examples that we showed, we can actually live with about 1% of the weights. So we only send 1% of the weights at each node. And this will still converge at the end. Of course, we remember the result locally. I mean, the error we are making, we remember locally, and then we accumulate locally. And every couple of 100 iterations, we send a full or reduce to make sure that we pick up all the noise. So we have shown this with a Microsoft speech production workload. So this is driving a very well-known speech assistant that I can't really mention, but this starts with a C and ends with an A. And here we drive down the training time from 2 weeks to about 2 days, of course, using relatively more resources. So this is the major result of the sparsification. Then we also show that we can gain good speedups on supercomputer type systems. But of course, supercomputer type systems have a very strong network, thus the speedup is less, because we can just send, we can just send it faster anyway. But we still get a significant. So now there is a second trick you can play in the communication. So this was just sending only the top k elements, but you could also send them asynchronously, as I mentioned earlier. So what we do here is, if you have imbalanced or unbalanced workloads in deep learning, so here, for example, if you have the different video lengths in a standard data set, or looking at LSTM models, or looking at even transformer models, you would see that they slightly vary, because in transformer models, the sentences are of different length. And as I mentioned, the videos may be of different length. So each node may have slightly different computational load. And in the synchronous case, you would always wait for the last node to finish. So you waste some computation just waiting for the slowest node. What you can do is you can actually use solo collectives that one of my postdocs showed this, Shigang Li, this year's PPOP conference, to implement that. And the solo collective is basically a collective where only one node is triggering the collective, and then asynchronously all nodes execute the collectives. So there's no waiting involved. And this leads to significant speedups as well. So this is another communication optimization, right? So it's another dimension. So we now give up on synchronization. And so we can achieve up to 60% speed up over Horovod, which is the state of the art. So now you may say, oh God, this is quite complicated. Now we listened for about 30 minutes to me speaking just about communication optimization. And I didn't really go into detail on any other hardware optimization to deep learning. In fact, that field is incredibly complicated. This is why we started a reproducible benchmark, because there's also a whole lot of confusion in this field that we call Deep 500. And the idea is to integrate with all these different frameworks that are mentioned here, like PyTorch, Caffe, and TensorFlow. And in case you are working on performance optimizations for deep learning, you should consider that benchmark because it first of all easily integrates with all these frameworks and allows to compare those, and it gives you statistically reasonable ways to show the performance, because that's not necessarily always the case in deep learning papers. So we have read a whole lot of those, and unfortunately the state of the art in the field is not as scientifically rigorous, let's say. So now I could talk a little bit more about actually the use of HPC, and I think I'll do this relatively quickly, the use of deep learning to help HPC, because so far I've talked about how can we use HPC techniques to speed up deep learning. But I want to give you a little bit of a glimpse of also what's going on in my lab for the other side. And the idea here is that we want to understand whether we can train a model that can analyze source code for us. And the observation is that we have a whole lot of code on public repositories. I mean, that's pretty obvious to each of us. And then the question is, can deep neural networks understand code? And of course, there have been previous approaches where they look at the source code, where deep neural networks look at source code and then have to deal with all kinds of idiosyncrasies of the target language, like Java versus Python versus C++. So you can see there are quite different languages. And what we did is basically we checked, or we investigated whether we can learn deep neural networks, or we can train deep neural networks on an internal compiler representation that unifies multiple languages. And the obvious candidate here is LLVM. So we took the LLVM internal representation, we faced it as a graph, as a data flow graph, basically summarizing the basic blocks and the data flow relations between those. So we call this the extended data flow graph. And now this thing is somehow hanging. Oh, the contextual flow graph. And then we use that graph to pre-train an embedding space for detection. For later tasks. So how do we pre-train this embedding space? We basically use the same natural language hypothesis that was used before, where you basically say that words close to a specific word form the context of that word. Now the question is, language is one-dimensional. How do we do this on this extended contextual flow graph? Well, here we do this by neighborhood relationships between graph nodes. And here, for example, this comparison node is neighboring to these branch nodes and this multiplication node. Then we train an embedding space, which is of the size of the vocabulary, just really the number of statements. And we choose a specific embedding dimension. So this is a little bit like an autoencoder. And then we can use that embedding space to train simple LSTM units for specializing to tasks like malicious code detection, guided programming, or program optimization, and optimal hardware mapping, which is most interesting for HPC. So the idea here, and now my laptop is still causing trouble. Oh, wow. So the idea here is that we can actually run this on an algorithm classification data set. So we get the highest accuracy in that particular task. And the question we are asking here is, we take the source code of a particular implementation of a function, let's say quicksort or heap sort, and we don't really know what that function is. And we want the deep neural network to guess from the internal representation what that network is, and we get a pretty high accuracy here on the standard data set. Furthermore, what we can also do is we can look at basic blocks of the code and predict whether they run faster on a CPU or a GPU, and then do this classification this way. We get also pretty impressive results, basically on par with previous publications that we've seen, like DeepTune and the publication of Greve et al. We can also look at optimal tile sizes for various target architectures. We can also guess them from the code. And the interesting thing is, we can even do queries, like we've heard with the normal language embedding optimization, or with the normal language embeddings, like this typical thing where king is to queen, like man to question mark, and then it'll tell you woman. And here we have similar analogies that we defined manually and then tested whether the network could do those. For example, multiplication on FP64 is like, FP64 multiplication to FP32 multiplication is like FP64 addition to question mark, and then it will tell you FP32 addition. And this is also actually working for this particular example, which is quite surprising, and fully automatically derived from a very large corpus of compiled codes. So with that, I would like to conclude this presentation and really mention that deep learning is largely HPC. The main bottleneck is communication. Communication is really an interesting trade-off between parameter consistency and parameter accuracy. This is very different from what we are used to in scientific computing, because there we do not have this trade-off. So this is actually the most important aspect of deep learning, or the most interesting aspect for research of deep learning. Of course, this causes a problem because the performance-centric view can be harmful for accuracy. So we can talk about performance without actually considering model quality, and then it leads to very strange results. Some of them have been published, and it's so aggravating me that actually I had to write a blog entry that's about the 12 ways to fool the masses when reporting performance. This is something I would like to close my presentation with, basically saying that if you work on deep learning performance, you should review that blog entry and check whether your papers make one of those 12 or have one of those 12 mistakes in them, because they're actually some of them are quite subtle, some of them are quite obvious. So with that, I would like to thank you and see if we have the opportunity to have some questions, even though I have no idea how this works here.
Okay, so here's a question from Olaf Zimmermann. GPUs are excellent for CNN, but have been reported to be less efficient for RNN, for example. Do you see any novel hardware architectures that would have a potential advantage over GPUs in these cases? Oh yes, so this is a very good question. There are actually lots of different hardware architectures developed or being developed, specific to specific networks. Like you mentioned, CNNs are running well on GPUs. I would actually also say that RNNs run reasonably on GPUs. And I don't know of any specific architecture for recurrent neural networks, but typically these are fully connected, so they actually have a much simpler computational structure in this sense. So matrix multiplication, and you only unroll them up to a certain size. So the units like GPUs, for example, should be extremely efficient for those. And also the tensor cores in the GPUs should be relatively efficient in these Volta GPUs. Mm-hmm. But I don't know any specific hardware developed for recurrent neural networks. But I could imagine that there is something. The market is so big. Okay, here's another question from Fahad. Hi Torsten, thank you for the wonderful talk. Quick question, do you see a difference in communication patterns between data parallel approaches versus model parallel approaches on HPC systems? Oh, that's also an excellent question. So yes, data parallel is basically all reduce. I know you will of course say, well, model parallel is, or what I call layer parallel, is also all reduce, but these are slightly different all reductions. In general, the data parallel all reductions are much bigger, so they have a much larger data size. And with those all reductions, this is either the model parameters you reduce or the gradients. Right? I have only talked about the gradients in this talk, but you could also reduce the model parameters. And if you reduce the gradients, you can play a lot of tricks, like I told you. In model parallelism or layer parallelism, you cannot play many of these tricks, or at least we have not investigated whether these tricks apply. So this is an interesting research area, I would say. So these are the main differences, but there's a lot of all reduce going on as well for fully connected layers. For an interesting one are different layer types, like convolutional layers. One of my postdocs had an earlier paper on how to parallelize convolutions. This is very similar to stencil computations as we know them from regular grids in climate. So there the communication pattern is substantially different. So it really depends on your layer type that you have, how you parallelize those. Okay, thank you. I see no more questions popping up. Last chance. Oh, there's one more from Bingong. Is there any approach or tricks that do not lose validation accuracy but keep the parallelization performance in terms of the training time?
Oh, so tricks that do, yes. I mean, these are the standard HPC tricks, I would say. So if we do not want to lose any accuracy at all, and this is now interesting, how do we define that we lose accuracy? Because there's an inherent noise in these calculations, meaning that if I choose a different random seed to just select the mini batches, I will get a different result. So this is why some researchers actually showed that if you drop more gradients, yeah, I mean, researchers, including us, we've also observed this. If you drop some gradients, like employ this top K method, your final result may be better in terms of validation accuracy than the one without. So it gets faster and better, but that's not generally the case. So if you want to get, this is why it's a bit complicated to define what better means or what validation accuracy. Like this is clearly defined, of course, validation accuracy, but depends on the random seed. So if you want to get the same result, right, so something like bitwise identical, then you could employ all these typical HPC techniques like optimization of schedules for reduction operations, for example. There's a whole lot of research in the good old MPI days how to do this, how to do very large reductions and how to minimize the latency of those guys, or how to do asynchronous reductions or non-blocking reductions. And this is probably the major optimization you could apply in terms of communication. And then, of course, also, if you do model parallelism, like I just mentioned, how to do these stencil-like exchanges, you could use neighborhood collectives in MPI, and they would also give you the exact bitwise result. So yes, there are some approaches. I have focused on the new approaches here in this talk, which are not so obvious to HPC people and didn't exist 5 years ago, I would say.
Okay, there are two more questions, one from Ernia. Hi, Ernia. Great talk, Torsten. Do you think that the future of deep learning hardware will be more based on the deep learning architecture that is used? For example, special hardware for DNNs and another special hardware for LSTMs.
Oh, that is also an excellent question. Actually, the interesting insight is that all of these layers, they can be modeled into tensor contractions. Right? So this is why the fundamental data type of any deep learning framework is tensors. And all you do is contracting them in different ways. And so now if you would design a hardware, because the hardware design is relatively expensive, right? You need engineers, hundreds of engineers actually, to tape out something in validation and verification and design. So I would expect that we would get a lot of specialized hardwares that specialize to these tensor contractions, and maybe applying nonlinearities, because this is another, so it's not everything is tensor contraction. You have to do a tensor contraction followed by some vector operations, which are then these nonlinearities like ReLU or GLU or all these various linear units. So I would say that if you find a good architecture for this, it would cover the vast majority of today's layer types, including RNNs, CNNs, fully connected, transformers, and all of these things that I would make up right now. Of course, the future may be different, because there may be things like graph neural networks coming up. These have more irregular structure. So they're also tensor contractions, but sparse tensors suddenly. And then it gets more interesting. But what's currently dominating the market, if you wanted to make any money with your accelerator, I would say, so you need to be careful about your return on investment. I would personally not specialize to particular layer types. Of course, you can always do this, but I don't think it's too much of a gain.
Okay, then we have one more question from MGIAR. Hi, Torsten, really nice talk indeed. Can you recommend any literature or comment on that deals with the interplay of the data pipeline and the model in the context of HPC? Thanks.
Yeah, this is basically why we wrote this survey. We didn't know any, and this is why we thought we created it. So this, I would basically recommend my own work or the other work by my postdoc. Besides that, I don't know. There's a very good overview paper by Vivian C. of deep learning hardware, which is more from a hardware perspective. I think if you read these two, then you will have a very good overview. over the field. And then there are tons of blog posts that give you the missing pieces on the new things, like transformers, for example, is not considered in our survey yet. But they would need to look at more modern things.
Okay, there are no more questions. Then I would like to take the opportunity to thank you very much again, Torsten. This was a
thank you.
Wonderful adventure. I think it worked out okay. And well, hope to see you again soon, and hopefully live and in person then.
Maybe, the virus crisis is over.
Bye-bye.